pleasure to start the third series of lectures. I'm very happy to introduce Jiaxu, who will tell us about constructing finite time singularities to some nonlinear PDEs.
Yes, okay, thank you so much for the invitation. I'm so glad to be here. And today's topic will be the constructing finite time singularities for some nonlinear PDE. So we're starting from the fluid equation, the compressible Euler and compressible Navier-Stokes, then move on to the Schrödinger equation, the defocusing nonlinear Schrödinger, and a little bit about the focusing nonlinear Schrödinger in the future. Okay, so the compressible Euler equation is a fluid equation. It describes the flow of ideal gas. So we consider a box of gas. The only force that apply on this box is the pressure, and this pressure is perpendicular to the surface, and we call it capital P. So the equation itself is derived from two conservation laws. If you let the rho to be density, U velocity, and P pressure, then the first equation you will have the conservation of mass. And the second is the conservation of momentum, the Newton's law. The mass times acceleration is equal to the forcing, and the right-hand side is the forcing negative gradient of pressure. So there's three unknown but two equations. So for the isentropic compressible Euler, you will have pressures, the Gamma's law. So P is equal to 1 over gamma times rho to the gamma power. And here the gamma is a physical constant that is greater than 1. So depends on different gas you are using. You are taking different constant. For example, for air, the diatomic gas, you take gamma to be 7 over 5. So the second equation, the compressible Navier-Stokes, is the compressible Euler plus some dissipation. So still, you can derive it from the conservation laws. So you have conservation of mass and conservation of momentum. And the only thing difference is in the conservation of momentum, in the right-hand side, you have extra mu times Laplace u. This characterizes the dissipation. And here, the mu is always positive to make sure it is viscous dissipation forcing. So in our work, we will always treat the this extra terms as a perturbation. So basically, starting from the compressible Euler and then go to the compressible Navier-Stokes equation. So this whole thing is about singularity formation. For the compressible Euler itself, it has two types of singularity. The first is shock, and the second is implosion. So for the shock singularity, it is where the solution develops some discontinuity, or at the pre-shock, the derivative tends to infinity. So for example, starting from a perfectly smooth curve on the left-hand side, and then after some finite time, it will have this tangential, at the origin, it will tangential to the vertical axis. So here's derivative is infinity, and there's a pre-shock happening. So to see this effect, you can go to this Riscal density and define the Riemann invariance. So first you raise the power to alpha. So you define a new variable sigma is 1 over alpha times rho to the alpha. And alpha is depends on the physical parameter is gamma minus 1 over 2. So it's always positive. So with this Riscal density, now you rewrite the equation, and now this becomes more more symmetry to each other. So all the terms on the right-hand side are the quadratic terms plus 1 derivative. And then especially in the 1D, we can do the Riemann invariance. So define W to be U plus sigma and Z to be U minus sigma. Now these two equations decouple with each other in the sense that the highest order derivative only depends on itself, doesn't depend on another variable. So these are two transport equations. So the standard way to study is through the characteristic line. And the shock formation is also easily seen from this characteristic line. So you can use this graph to make some illustrations. So you have two family of characteristic lines. So when they are intersect with each other, you may have a shock because along each characteristic line, the value is conserved. So here are some literatures about the shock formation. So it's starting from the smooth initial data and developed shock, because our focusing is on the implosion. So I will not mention a lot about this results, but the idea is you're starting from 1D and then go to the higher dimension, and you're starting from the radial asymmetry to extend it to non-radial asymmetry initial data. And this whole thing is also happen in the implosion and also the Schrödinger equation as well. Okay. So what about the implosion results? So the implosion is a much more singularity line in the sense that the density itself tends to infinity. So here is a picture about the implosion. So left-hand side is the density, is smooth and bounded. After some finite time, it starts to concentrate in the middle, and at some capital T, the density is infinity at origin. So this is implosion. So the good way to find implosion is through the self-similar solution. So the self-similar solution itself will look like this. So with time change, the solution will not change shape. The only thing it do is to scale along two axes. So in this picture, it will compress along x-axis and stretch along the vertical axis. And the capital T here is the blow-up rate. It's the time that you want the solution tends to infinity. And the lambda 1 and lambda 2 is a constant that you should fix it through scaling. And usually there's some flexibility, as in our case. So especially when people impose the radially symmetric assumption, then the good thing about self-similar solution is that the PDE now becomes ODE. So you can use all the method of ODE to solve it. And as long as your parameter is chosen well, so you will have the implosion. So as you can see here, if you let the x to be 0, then rho evaluated at 0t is the capital T minus small t to the lambda 1 times this profile function, capital B bar evaluated at 0. So as long as the lambda 1 is negative and the profile function is non-vanishing, then this will tends to infinity as time tends to capital T, and this is where you have implosion happening.
In any dimension?
There are some results are any dimension, and usually it's greater than or equal to 2. So there's no 1D. Yeah, 1D there's no blow. Yes, there are 2, 3, and also others. So our results about 3, and there's results the Marfell and Xenfell, they do D greater than or equal to 2. So depending on dimension, they may have slightly different behavior, but yeah. So there's results covering. Thank you. So the way to find a self-similar solution is to do the rescaling along the coordinates. So now this is in new coordinates. We write it in, it's called self-similar coordinates, S and Y. So this coordinate is chosen such that it's moving with the self-similar solution in the sense that the self-similar solution now you can treat it as a stationary solution in the new coordinates. So because the self-similar solution only have the scaling effect along axis, so when you do this coordinate change, you basically have two terms which we marked in blue here. Those are coming from the coordinate change. The first term is a decaying term, and the second term is the trajectory term, y dot gradient. And these two will coming from the coordinate change. And the black terms are the compressible Euler terms. They are just coming from the compressible Euler equation. So now you have this new equation, and the self-similar solutions are just stationary solutions. The partial S U bar is equal to 0, and partial S bar is equal to 0. Okay. So here are some literatures. So Gertley first studied those self-similar solutions, basically solved the ODE and imposed the radial symmetry assumption, and found the non-smooth radial self-similar solutions. This is around 60 years ago. And then until very recently, there's Malrafil and Stafel result they find for first C infinity smooth radial self-similar solution for almost physical parameter gamma greater than 1. So it depends different dimension, they may have different variation of this blow-up parameter. So in their case, they only know that this exists for almost every physical parameter gamma, but so the thing that they don't know is what about the gamma is equal to 5/3. This is a degeneration point in their study. And also the thing is not for sure is which gamma doesn't work is also not known from this result. And then there's result from Tristan, Gonzalo, and Javi. They show that in the compressible Euler, I think this is only for 3D. This holds for all, there's C infinity smooth radial self-similar solution for all the physical parameter gamma greater than 1. This is another groups of profiles. So related to a different family of parameters. So we'll talk about this in details after this slides talk. So, and specifically for the gamma is 7 or 5, this diatomic gas case, they find the same group of profile in the Malrafil and Stafel case. and show that there exist C infinity smooth self-similar solutions. So for the degeneration case, the gamma is 5/3. This corresponding to monatomic gas. This work from Shao, Wang Wei, and Zhang Wei show that there exists a C infinity smooth self-similar solution. So those are all the profile, the exact self-similar solutions. And as we mentioned, those are just ODE systems. So here the U bar R is the radial component of the velocity, and the dimension is D. So you want to find self-similar solutions, you solve this ODE system. Well, it looks not that hard, but actually it's very complicated. So the way to do it, people use the phase portrait. So this is not autonomous system, but you change coordinates and this will become autonomous systems. Then you have the following phase portrait to solve the ODE. So you have the, so this is phase portrait, and if you want to find the C infinity self-similar solutions, the way to do it is to connect these 2 points. This P infinity and this P0, one corresponding to the origin and one corresponding to the infinity. And then you'll find that if you want to connect these 2 points, you will inevitably cross this red line. And the red line corresponding to the singularity of the equation. So the equation itself can be written as the derivative is equal to numerator over denominator, and the singularity happens where the denominator is equal to 0. And the green line are those numerator is also equal to 0. So the way to cross it, but without losing C infinity smoothness, is to cross this PS point, this sonic point. And only when you cross this through 2 specific directions, you may be able to find C infinity smooth solutions. And only one of them gives the globally C infinity smooth solutions. And so there's complicated trajectory and barrier arguments going on to connect this to P infinity and P0. And if you want to work it for and there's a freedom to choose gamma, so you want to fix gamma, and also there's another way. Another thing to do is to fix the blow up rate small r. So this self-similar parameter has to be fixed. And in principle, there's only a sequence of them should work. And we will also talk about this in details later. So this is about the phase portraits. And what about the Navier-Stokes equation? So as we said, we want to use the compressible Euler equation to solve to find the implosion for the Navier-Stokes equation. So notice that the Navier-Stokes equation will have extra term. This is mu times Laplace u. So the idea is you want to, in the self-similar coordinate, this term should be negligible or have an exponential decay. So if you write it in a self-similar coordinate, this extra term will pick extra exponential decay or exponential growth effect. Like we marked in green here, this e to the negative delta dissipation s. And this delta dissipation will depend on the small r, which is the blow up parameter, the one that you can choose. And well, you cannot choose anyone because not everyone corresponding to a self-similar solution. And the small alpha is determined by the physical parameter gamma is greater than 0. So only when this is positive, this is a perturbation formally. And then there's where, in principle, it can be treated as a perturbation. So now I'll talk about different stability behavior, because the way to treat it is you write it as a perturbation plus the U bar and S bar. Those are self-similar solutions. And then you put it in the equation to see if there are some, those U tilde and S tilde will tend to 0. So if for any arbitrary initially perturbation that is sufficiently small, you have the perturbation tends to 0 as time tends to infinity. This is the full stability result. So it's also the usual stability that we are saying. So the thing that we got in the literatures here are all the finite codimension stability. So there may exist finite dimension that is unstable, and only when your initial perturbation that is sufficiently small and also some certain projection to the unstable mode is equal to 0, their perturbation tends to 0 as time tends to infinity. So you allow there's finite dimension that is unstable, but you want to moderate out. And this is, in principle, a highly unstable profile, because as long as you have one unstable direction, of course, you have infinitely stable direction that you can perturb from. But only when you perturb to the stable direction, you have the green direction, you have this stability results. Well, if you perturb through the red direction, they will have the component that is non-zero in the unstable direction. And through all this red direction, if you only have the finite codimension stability, you cannot see anything. So with probability 1, you do a random perturbation, you will not be able to see this stability and this blow-up effect. So if you have finite codimension stability, that is super unstable profiles, and it's very hard to see in the experiments. So here's are the literatures on the stability behavior. So after their works on the C-infinity smooth self-similar solution, Muller-Raphael or Netsky and Sefel, they use the stability argument to show the radial symmetric implosion for compressible Euler and Navier-Stokes. And for the gamma is equal to 7/5 case, Tristan, Gonzalo, and Javi, they also show the stability result, and there's implosion for Navier-Stokes. And the different thing they do is they perturb the solution such that it has a positive but constant density at infinity. So in this case, their implosion, they show that the implosion isn't caused by the vacuum. And then we will start to considering if there exists a non-radial implosion. So basically we do the non-radial perturbation near the radial symmetric self-similar solution, and to show that in 3D there exists non-radial implosion for compressible Euler and Navier-Stokes. And then there's work from Jajic, Shaldi, Skobler, and Vickel. So what they do is they do the 2D AC symmetric setting only for the compressible Euler, but they do a small swirl near the radial self-similar solution, and those swirl will create vorticity. And they show that not only the density will blow up, but the vorticity will also blow up in this case. So in the radially symmetric, the vorticity is just 0, so there's nothing there. And then Jajic extended this regime to the high dimension, like the dimension is greater than or equal to 2. Use this as a symmetric structure in the compressible Euler case. There's also vorticity blow up. So those are the stability results. So here I mark our results here. So there exists finite codimension, non-radial smooth initial data such that solution to the 3D compressible Euler and Navier-Stokes develop an implosion singularity. So the way to do it is to stability argument and show that this perturbation always can be controlled if you module this finite codimension, possibly unstable mode. Well, but still, no people has proved there exists unstable mode yet, but people guess that is the case, and there's numerical results. Okay, so why we do study the non-radial implosion result? So compared to the radial setting, the non-radial implosion is a multi-dimensional problem, so it's posed some difficulties. And then also the first thing we want to actually do is to do it on the torus, but we find that in order to do it on the torus, we have to do the non-radial perturbation because the compressible Euler may be fine, but compressible Navier-Stokes, there's a Laplace. So if it will inevitably, you cannot use the finite time propagation, and so you have to use the fully non-radial setting. And after we do the whole space case, we do the torus just by a smooth cutoff, and you can do that. And then also, this part we didn't do, but we think this can be done, is to construct blow up at multiple points. So you glue some solution that blow up together, and then it may simultaneously blow up at different points, because the only thing that matters is the things near the blow up points. So why there's stability? So actually, the stability is coming from these two terms, which is given by the coordinate change. So if you still remember, there are two blue terms in the coordinate changing term, and the one is decay and one is trajectory. So these two equations can be solved directly, use trajectory argument. So along this blue trajectory, you will have exponential decay with respect to r. Small r is always greater than 1. So this is a full stability if only consider this system. So all the stability arguments for this compressible Euler is to show that these two terms will actually control other terms in some sense. So of course you need some properties for the self-similar solutions to make sure those things can be controlled. So the two most important properties are the repulsivity. So those two things are positive, cross be greater than a constant. And the first one is used in the radial setting, and you need both in the non-radial setting because the first one will control the radial part of derivative, and the second is the non-radial, the angle part of derivative. So we will write down all these energy estimates in the later lecture, and you will see how it works there. So the structure is to use this argument of the maximally dissipative operator. The same for all the non-radial and radial work. So there are two things. Show that the first part is the energy estimates. The real part of the operator x and the inner product of the ax and x should be negative. And the second is called the maximality. For sufficiently for all lambda greater than 0, or actually for sufficiently large lambda greater than 0, the lambda I minus a is surjective. And then from this, the Lummer-Phillips theorems show that if A is maximum dissipative operator, and then the domain is dense, then it will generate a contraction semigroup. So the finite codimension setting is up to a compact perturbation. This is a maximum dissipative operator. And then there's only finite codimension that is not good. So those are the things need to be done. So for a finite codimension subspace, you have the real part of the inner product should be less than or equal to -1 times it, or some negative constant. And second is the maximality. So for sufficiently large lambda, the operator minus lambda I is surjective. So if you have both two, then from Lummer-Phillips theorems, you already split the space into this invariant subspace, the stable space and unstable space, such that the unstable space is dimension finite, and in the stable space you have contraction semigroup, and in the unstable space you have this generalized eigenvectors. Their eigenvalues are large. So there's a spectrum gap. So the last one is the unstable space only consists of C-infinity smooth functions because you want to have a smooth blow up. And then you project the initial perturbation into the stable space. So the projection itself have to be smooth. So the unstable space should also be smooth as well. So the most important part will be the energy estimate. We will talk about that in details. So for the Navier-Stokes, as we said, this can be treated as a perturbation. And this is formally guaranteed by the fact that there's exponential decay here. But, well, as you can see, there's a 2 derivative on this perturbation term, and all the compressible Euler term, the black terms, there are only at most 1 derivatives. So there's natural questions why there's no derivative loss. So for the Navier-Stokes case, it's just because this extra dissipation have a good sign. And the thing when you do energy estimate, this cosine will give you a negative term. It will not damage whole decay. So now those are all I want to talk at the first round about the fluids. And then we'll introduce a little bit about how to connect the compressible Euler to the defocusing nonlinear Schrodinger equation. So here's our defocusing nonlinear Schrodinger equation. As you can see, it's a complex equation. So the V is a complex function. And then this capital P is odd integer to make sure everything is smooth, and it's also greater than 1. So for these equations, there are 2 standard conservation. The mass conservation, the L2 is conserved, and the energy conservation is this homogeneous H1 plus some P plus 1, LP plus 1 norm is conserved. Okay. So if you do the scaling, the critical solid space is HSC when the critical when the critical component is equal to dimension over 2 minus 2 over P minus 1. The P is nonlinearity and D is dimension. So when this is less than 1, is in the energy subcritical regime. So in this regime, if you have the smooth initial data, they have global existence plus scattering. So the scattering means the solution will tend to the linear Schrodinger equation. The nonlinear term doesn't play a super important role here. So for the critical space component is equal to 1, we are in the energy critical regime. So still you have the global existence plus scattering, but things are more complicated and delicate in this case. So the thing is first done in small critical norm, and then proved with the radially symmetric assumption, and eventually generalized to all the general initial data without radiality. And they first, so as you can see, they only holds for dimension greater than or equal to 3, because if you plug in here, the dimension less than or equal to 2 is always in the energy subcritical regime. So you don't need to work on that when you are in the critical regime. So what about the energy supercritical regime? So this is, people have long conjecture that the global existence still true because you have not only mass conservation, the L2 conservation, but also the H1 conservation. So it's a really strong conservation law. So why this thing should blow up? But actually, there's work from Muller-Raphael and Science-Fail. So still after the work of compressible Euler and some stability arguments, they show that the radial implosion exists for such parameter, the dimension NP. And we extend this to non-radial implosion. So pick one of this dimension, one of P, and show that there exists non-radial implosion. So the way to connect this Schrodinger equation and the compressible Euler is through this standard modulus transform. So the V is a complex function. You write it in the modulus and angle. And the modulus is the square root of density. And the angle, the gradient of angle is velocity. So if you split them and plug into the equation, take the real part and the imaginary part, you'll find that this satisfies the compressible Euler, except this orange term. So this is very similar as the never stop because there's extra orange term which may potentially treat it as a perturbation. And even better, this is actually a potential flow because it's a gradient of angle, so it's actually irrotational compressible Euler plus perturbation, if the parameter is chosen correctly. So then the same thing happening, run the self-similar coordinate argument, and the extra term pick up a self-similar effect. So in this case, it's 4 minus 2r as the coefficient. And you have to make sure the small r is greater than 2 to treat it as a perturbation. And so that's why they can only do dimension is greater than or equal to 5, because whenever dimension is less than or equal to 4, there's no way you can choose r greater than 2. So let's compare the defocusing nonlinear Schrodinger and never stop, because they are all one terms perturbation of the compressible Euler. So we mentioned this before, this extra terms in the Navier-Stokes is controlled by the sign, the good sign of the Laplace U, the highest derivative term. But if you want to do the same thing, like in the L2 norm or some other norms, use this integration by part tricks, there's no way you can get a sign condition from it. So still have derivative loss, and there's don't go into anywhere if you just do this. So this actually tells you that this energy for the compressible Euler is not the energy for the Schrodinger equation. You have extra terms in the energy estimates. So this happens for both the radial and non-radial. In our work, we introduced this logarithm density and to simplify all these energy estimates. So basically, you define the log, the W as the 1/2 of log rho. Then this extra forcing term is just this linear term, the gradient Laplace W, plus this gradient plus the quadratic term, gradient of gradient W squared. In the sense that this W itself is both satisfies a good enough equation, only have quadratic, linear, and constant term. So there's no complicated nonlinearity happening here. And then instead of running 2 equations and finding the energy, you can actually run 3 equations together. You put them as a system, just ignore the fact that S are actually completely determined by W. They are related. But with these 3 equations, there's a natural energy. And for this new energy, there's no loss, but the weight has to be chosen careful. This rho is the density. You have to fix this weight, and this weight will give you the no derivative loss. And the first 2 terms are just compressible Euler energy, those homogeneous HK of the U and the HK of the S. And the last term is this correction term for the defocusing nonlinear Schrodinger. And if this K is equal to 1, this is the H1 Sobolev norm, conservation law of the Schrodinger equation. So that's how to treat the conservation law. And we'll also write down this cancellation in the lecture. So of course, the open question is what about dimension is equal to 3 and 4? So this cannot be done because the parameter, there's a sequence of parameter that may work, and it will tend to a limit. And this limit will always be less than the limit, and this limit is exactly 2 in the dimension 4. So dimension 4 is critical case, and the dimension 5 is slightly above, so it's okay. So what about the focusing case? So the focusing case, of course, there's many blow-up results happening, but you can also apply the modulus transform to the focusing nonlinear Schrodinger. So for this equation, they have mass conservation and energy conservation, but with a different sign. So even it's conserved, there's no guarantee that there's H1 norm is bounded. But from the mass log transform case, you do the same thing because there's only sign changing. So the transformation is still same and it leads to a fluid equation as long as you let the u velocity to be the gradient of angle and the density to be the modulus square. And the only difference between the compressible Euler and this new fluid equation is that now you have a negative sign. This we marked in red here. So in the self-similar coordinates still, you have this exponential effect going on, and potentially you want to treat this as a perturbation. So the R want to fix it to be greater than 2. So we want to study this case. The motivation, of course, for the focusing case, when you are in the mass critical and mass supercritical case, there's virial identity showing the blow up. But we want to show if there's a connection to find the potential blow up to the focusing case through this fluid equation. So what we already done is we study this fluid equation and we find the self-similar solution for this equation. So just neglect the forcing term and to find the phase portrait, and this is radially symmetric. And so this is an ODE system and you can solve it. So as long as this parameter satisfies through this way, you have the C-infinity smooth self-similar solutions. So the small r is blow up rate. So in principle, you want to make sure the small r is greater than 2 to treat the extra term as perturbation, at least formally. So this gives you the left-hand side should be greater than 1. And this is mass supercritical case. So this also a little bit connected to the focusing Schrodinger equation when the blow up may happen. Yes.
So this is a difference with the other subset.
Yes, there's a sign difference. This plus is negative. That's compressible Euler. This is another fluid equation. Yeah. Yeah, the way to do it is same. You do the autonomous ODE and there's a fraction. But the good thing is now the denominator, as we mentioned in the compressible Euler case, the denominator will be vanishing and causing some singularity. But here it's not vanishing, it's plus. So all the estimates are much more easier and you can use the phase portrait to see the results. So the green line is the starting of the phase portrait. So there exists one that, well, tends to this 0 is the endpoint that we want. And this red line is serving as a barrier. So when the parameter is chosen incorrectly, as we said in the theorem, then the barrier argument shows that all the things will converge to 0. And there's another attracting point here. So if the parameter is not correct, may go there, and this is not the thing that we want because the endpoint doesn't work well. Okay. So of course, for this future works, so the potential application to the focusing nonlinear Schrodinger and how to treat the perturbation is really as a perturbation. So here's the problem is that for this fluid equation is actually ill-posed. The sign changing will damage all the energy estimate stuff. And now in the Sobolev space, you cannot have well-posted results. And the only well-posted results is you want to impose some analyticity because there's derivative loss. And then to control it, there's also the lack of energy estimate because the sign of the focusing Schrodinger, the energy estimate in the focusing Schrodinger equation is different as the forcing. So this makes it harder to control in the stability arguments. Yes. Not in the Sobolev space for this fluid equation. So for the Schrodinger you have, but for
even short time.
For the fluids, yes. Even short time you don't because the sign is different. So when you are decoupling, this actually like the Cauchy-Riemann equation. So it's I yes, the I. For focusing Schrodinger, of course, there's local well-posedness in the Sobolev space, right? Because there's no derivative loss, there's just loss.
Even this large P, even when it is very high nonlinearity.
Well, I think there won't be any problem, right? Because it's local well-posedness. So if you get it very smooth, and then the only thing that you do the energy estimates, then you just even if you have nonlinear estimates, it's bounded locally in time, so it's still okay. The p doesn't matter. I think for the local behavior, but global, of course, it will matter a lot. Yeah.
Does this mean that
Yeah.
you would have a kind of well-positionists with more assumptions on the data? Because, like,
Yeah. That's what we guess. So if you have some analyticity of the initial data, well, of course, the fluid equation is good. And when you split it into this like Cauchy-Schwarz type equation, then you have to choose it. Like maybe there's a way that to project it to some subspace such that actually the local well-postedness is good. Because the Cauchy-Schwarz equation, like it's always there's one direction is good. For example, the imaginary part is some Hilbert transport of the real part, and then it may just give you some good things. Yeah.
I was thinking more just from a higher Sobolev.
Yeah. Oh, the Sobolev space probably not, because this equation itself it just doesn't work. I think how to. Let's see, the good way to think about it is, let's see. So the derivative loss is coming from partial as u. I will omit all this u term. This gives partial ys. And then partial ss is negative partial yu. So let's consider it in the 1D. This thing's easier, and it's already have the derivative loss. So I just eliminate all those terms because these terms in principle there can be done with integration by parts. So there's no derivative loss. And I only keep these two terms where I put this to be 1 and this partial y and this is negative partial y. So this will gives you, and this is the model that may give you the derivative loss for this. So the derivative loss can be seen, so it's and this gives you negative I guess. So this is Cauchy-Schwarz, and of course there's another one. So when you decouple this system, so now the u plus is only depends on the derivative for u plus is and not u plus minus is. There's an I here. So if there's an I, there's no way that you can do it in the sublet space. In general sublet space, some subspace may work, but not general. Yeah. Okay. So that's the lecture of the first part. So I want to give an overview of all those things, and we go to the second round to do it on the board with more details. And okay, but first, any questions? Yes. Oh.
In the regular Euler problem.
Yes.
When you're looking for the self-similar solutions, you get the space portrait.
Yes.
You have this kind of event contour where denominator
Yes.
is 0. What's the physical significance of that? Is that a transition from sub to supersonic flow or something else?
Yeah, I think those are actually I'm not super familiar with of this part, but this will corresponding to this. So if you run it in the kind of, so let's say do it in the radially coordinates, and there's a kind of Riemann invariant kind of stuff. So when you decouple the whole system, this actually the thing is the coefficient. Let's say it will give something like this, I believe. This is radial coordinates, and this is u, and this is alpha s partial y u plus s plus something. There's no derivative. And of course, there's another one that's corresponding to another Riemann invariant. So the lower terms are terms without derivatives, and the 0, 0. So this one of them is 0. I think it's probably this one is 0. Yeah, so that's the physical meaning line. If you do the trajectory line, this is 0. Yeah. And also you can see the singularity from here, right? Because the stationary solution is just this, both left-hand side is equal to 0. And now you cannot recover the derivative from the lower term because this is equal to 0. And then that's what something bad may happen. Yeah. Yeah. Other questions? Yes. Oh, sorry.
You're saying this is open, so this is like not symmetric. It's like if you think about this as like a symmetric kind of problem.
What do you mean by not
Sorry,
symmetric?
like well close to this or this fluid.
This fluid equation?
Yeah.
You mean the this compressible Euler? They are not symmetric. Yeah, they are not symmetric because U is like in high dimension. The U is just main dimension, right? This S is just a scalar. One is velocity and one is density. So of course they are not symmetric, but in the 1D you can see the symmetry. Like in the scaling sense, they are symmetric, but they are projected plus 1.
Right. So that's where the well close to this. So like the well like for that.
Oh, the model equation. This is for another one, right? This is for the focusing. This is not compressible Euler. I just use this to explain why there's derivative loss for this equation. Yeah, this one, without this orange term. So, why there's derivative loss for this equation?
So is this like other negative pressure or like when you flip the sign?
Yeah, this is negative pressure. Yes. And yeah, of course, this is high dimension, but well, this derivative loss already can be seen from the 1D, and the high dimension doesn't make any difference because we can always impose radially symmetric assumption, and then all the derivative loss will happen as well. Yeah.
Yes, it's a little bit about focusing NLS. You had one slide about the existence of the self-similar solution for very specific parameters.
Yes, this parameter.
Yes. So
Yes, it's holds for P and D, all the P and D.
it's an exact self-similar solution.
It's for this is exact self-similar solution. This is not exact for focusing Schrodinger because there's one term is not there, but for this is exact.
It's exact for focusing NLS.
No, it's not exact for focusing NLS. It's exact for this equation, and this equation is not focusing NLS because focusing NLS is there's extra term here.
So this is for another model.
It's a model fluids equation, but not focusing. Yeah.
So what can you say about knowing this? What can you say about focusing NLS?
So there's only potential thing you can say, right? So you know in compressible Euler self-similar solution, you connect it to the focusing on Schrodinger and find blow-ups here. But knowing this is the same way as the compressible Euler do the defocusing on Schrodinger. So if there's some stability argument can be done, then it may translate this profile into another blow-up profile for the Schrodinger equation, focusing and is connected to the fluids.
And has been, do people have done some numerical simulation to test this question?
For this, no.
Or it's too hard?
No, for this, no. I think, yeah, no. Yeah, I think this is, we did it on March or something, probably. So this one is, so for this new profile, still relatively new, and we didn't really do the numerical to see if it works yet. Yeah, thank you. But it's a good idea. We should try. Yeah, but numerical is probably hard, right? This, if it can be done, it's still at least finite codimension and probably infinite codimension stability. So I don't know how. Yeah, yes. Yes.
One more back to the self-similar Euler
Yes.
profile. Is it believed that there are radially symmetric unstable modes?
Yes, it's believed. I think several people are working on that. There's still no rigorous proof yet. Yeah. So let's do the how to here. Right. This one. Oh yes. Thank you. My notes. Yes. Okay. Okay, so let's do more details. Okay. So starting from the compressible never stocks. Actually, of course, we are first working on the compressible Euler. The equation for the velocity and the equation for the density. So here the gamma is greater than 1 and x. The space can be either in the torus or the whole space. So the first thing is to change the rescale density, and then we let the small alpha to be gamma minus 1/2. And this is the rescale sound speed. This is 1/alpha times rho to the alpha. So now instead of finding the equation for u and rho, you derive the equation for u and sigma. And the equation for u and sigma will be look like this. So the pressures become sigma gradient sigma. The gradient pressure becomes sigma gradient sigma. And this mu is a different mu, but for the simplicity, we just put it as the same mu here. So this is the rescale density version of compressible Navier-Stokes. So for the self-similar solution for the compressible Euler, the scaling will look like this. So uxt is this. So we have one parameter family that you can choose, which is small r. It's always greater than 1. Yes. Where? Then. Yes. After rescaling, there's only sigma. There's no. Yes. Yeah. This capital U is the profile function. And now we just write it into the self-similar coordinate. So it's still not self-similar form yet because your time will be a logarithm. Well, the self-similar change itself doesn't matter if you have viscosity or not. But if you plug in, you'll find that if you put this mu doesn't equal to 0, you will have exponential effect on this equation. That's the only.
So this formula is valid for Navier-Stokes?
No, this value for everything because this is just a change of coordinates. It's not a self. Yeah. So for the profile of sigma, we call it capital S. And the small r is always greater than 1. Well, could be have more restriction. So this is the new time variable. This is S. And this is Y. So from now on, the derivation will be the capital UYS and capital SYS. And the S. So if you want the small t to start at 0, your S is actually start as this capital T logarithm of capital T times -1 over small r to infinity. And small y is the self-similar space coordinates. Of course, it's still in the whole space when your x is in the whole space, but for the torus, it's actually expanding self-similar coordinates because you divide it by the time effect. So for this y, this boundary is not fixed. And the way to get the stability down, this small s should be chosen. The starting point will be large enough. So this corresponding to blow up very fast. T is very small, then the small s is super large at the beginning. So this is what we call S naught. Well, this doesn't matter for the compressible Euler, but for the Navier-Stokes, you will see this effect coming out when the S naught should be chosen large enough. Then we can plug this two into the equation, and this will give you the equation in the self-similar coordinates. Now we have capital U. I'll put the gradient term together. So this is the Navier-Stokes thing. And as you can see, other terms, there's no exponential effect, but so only Navier-Stokes terms will have exponential effect. So Dirter dissipation, this can be calculated and directly related to the blow-up rate and the small physical parameter alpha, and this should be positive. Okay. And then we'll go to the self-similar solution for the compressible Euler. So basically, these two are 0, and this is dropped. down. So we call it U bar, let's say. This is a vector equation, and the second is a scalar equation. So then, of course, we impose the radially symmetric assumption. So this U bar is only radially symmetric, so it only has the radial component. So let's R to be the radial components, the radial direction. And you have this. So this is the one that we wrote on the slides. And from now on, I will restrict the dimension is equal to 3. Of course, you can do the same thing for other dimension as well. Okay. So the next step is to change it to autonomous system. To change it to autonomous system, the changing is like that. So basically, you do the UR e to the c divided by e to the c. So you change the r to e to the c, and this will be your new coordinates. And the way that's make it easier, you can write the w c as this some combination to decouple it a little bit. As r to the c and z. Is minus. So this is a mimic of the Riemann invariant. So you have u plus s and u minus s. But to change it to the phase portrait or the autonomous systems, you use this. This will already be changed. So let's do it like do example. Do the first one, and you can see how it works. Let's say for 1. So just change coordinate, u r e to the c, and let's first don't do divide. And then this will give you e to the c. And the second term is same. So now it's derivative with respect to c instead of derivative with respect to r. And then you just divide it by e to the c. You will see that this is autonomous. At least this equation is autonomous. Second term will be it. see. Yes. Zeta is e. Yes. Yes. Zeta is my new variable, and you want to divide it by z e to the zeta as well. So basically, SR divided by R and UR divided by R, and change the R to e to the zeta. And then there's no, so all the things are grouped together. So this is autonomous system. Nothing left. And you can do the same thing for the second equation as well, and it will be autonomous. So especially if you do this plus and minus, well, this doesn't change if it's autonomous or not. It just makes things a little bit easier. And should I keep this? Maybe I will keep this. So let's write down the full equation. As we said, it will be a fraction because you want to divide it the same incremental derivative to the right-hand side. So everything will have two parameters. One is the one that you don't know, the blow-up rate, small r. And the one that you do know is the physical parameter, small alpha. So if you write down in this case, it will be quadratic over linear fraction. So we call it NW over DW, the numerator over denominator. And another one, slightly different, but still numerator over denominator and quadratic over linear. Easy. So the singularity will happens when the either NZ dw is equal to 0 or dz is equal to 0. So let's draw a simpler version of the phase portrait. Just so this is negative infinity. This is 0. Horizontal is w and the vertical is z. So P infinity is 0, 0 right here, and P0 is something here. And of course, those dz is just linear, but if you do the complication, this will be a curve. It's another color. This is the denominator equal to 0. And you want to also cross the same point as the numerator is also equal to 0. This is ns equal to 0, and you will have ps. So solution is something like you connect P0 and PS, and then you go to P infinity. So way to do it is you can do this either half relatively easily. So there exists one unique line that connect PS to P0, and there exists a family of curve connect PS to P infinity. But at this point, they may lose C infinitiness because this is actually corresponding to a 2x2 system attracting node, and there are infinite many curves will converge to that. So this is very tricky, and we will talk a little bit more about it.
The white line is what? What is the white line?
The red line.
What?
So potential solution. The solution curve. This one?
No, the straight one.
Oh, the straight one is just this the region that you want to consider it, because now you change the coordinate to be Z is U minus S and W is U plus S, and S is density, so it's always positive. So you're always below here. Yeah. Yeah, but if you write US, it will be the whole parts.
And then the white curve that you are just showing now.
Yeah, the white curve, I just want to show that the solution will almost look like that. This solution. Yeah. Oh, I should make it dot line. Yeah. So because you want to connect all these 3 points and to make sure it is C infinity smoothness. Okay. So the most important issue is actually happened at PS, because at this point, it's actually infinite many curve will intersect at this point. It is attracting node, as you can see. So let's study this more detail. So partial zeta is NW over DW, and partial zeta Z is NZ over DZ. So at PS, this will tend to 0 at PS. This will also tend to 0 at PS. So this is where singularity happening, and this is not equal to 0. So W is always smooth, but Z may have some singularity happening. So to see this fact that is actually attracting node, you do some coordinate change. So change coordinates. For the new coordinates partial phi, basically we time negative dw dz on both equations. So this will not change the solution curve itself, it's just change the parameter. So now because both nz and dz, they are equal to 0, so at PS. So this is, for this new system in the new coordinates, is actually a critical point for this 2x2 system. It's a nonlinear 2x2 system. And we know that from the standard ODE class, you know that the 2x2 system will characterize by the linearized part as critical points. So you take linearization, and there's eigenvalues, eigenvectors, and eigenlines. So at this point, so the classification of it will be the attracting node. Another pad.
What is psi?
Oh, sorry. The psi is just change it. Like you can write it, but it just times dw and dz on both sides of the equation. So the slope field doesn't change, right? So it's the same slope field. It's just you change the altitude. So the most important things as the critical points should be the eigenvalues and eigenvectors. So why there's a sequence that's actually corresponding to the eigenvalues. So if you still remember, in the slides we show there's a v minus and v plus. They are the eigenvector directions. Well, those things are all depends on two parameters, the physical parameter gamma and the law of small r. This two. Yes, for this one. So now there's no singularity. It's just everything is this nz times the nw times dz is a polynomial of order 3, and this is also polynomial of order 3, and those two are critical points. They are equal to 0 at this PS. So do the linearization near this point, you will see how locally it behaves. It will have two eigenvectors and eigenvalues for this linearized system, SOD. Okay. So for this, you can define a function which is, let's fix gamma. Let's see. Fix gamma. This physical parameter is fixed and define k of r as the larger the lambda minus over lambda plus, and the lambda minus is the one with the larger absolute value. So they are actually all negative. So because your gamma is fixed, the only thing you can change is small r. And when the small r is equal to 1, we have k of 1 is equal to 1. And we say that there is a sequence of parameter, and the limit of the sequence is where this k of r tends to infinity. So basically, lambda plus will tend to 0, and this will tend to infinity. And this will be a monotone sequence with respect to r. And now you can see let's draw the picture before we write down what is r star. It's a complicated function related, well, not super complicated, but some function related to r. So let's just consider the linearized system. So locally, for example, the critical points is PS as origin. You have, let's call it V minus, and let's call it V star. And because it's attracting node, so it should look like this. So why there's only two C infinity smoothness direction. So this actually depends on the ratio of the eigenvalues. And just for the linearized system, your solution, let's see, we call it VT, is C1 e to the lambda 1t times v1 plus c2 minus t minus plus c2 e to the lambda plus t plus. So for example, your v minus is 1, 0. And v plus is 0, 1. Then what you get, the thing you get is v of t is c1 e to the lambda 1t and c2 e to the lambda 2t minus. So if this curve is smooth at origin, will depend on the ratio of it. So this gives you x is y to the lambda 1 minus over lambda 2 times a constant. Whenever those are lambda minor, so let's say lambda minor is larger at absolute value, whenever this k of r is not integer, there are only two smooth directions, even in the linearized system, which corresponding to the two eigenline directions because they are straight line. And other directions, these curves are only ck of r smooth. So if k of r, which is lambda minus over lambda plus, is not integer, for linearized system, there are only two smooth directions. Of course, you may want to ask what happens if it's integer. Well, this is for the linearized system. For the nonlinear system, the integer will be not good because we will write down the recursion formula and this will give you a denominator equal to 0 when you have integer case. So now let's write down the r star. So what is the r such that this thing is infinity and what is the recursion formula just in an abstract way? So how to get the recursion formula, you just do the Taylor series expansion and to match all the coefficients and to pull the highest order out and then you'll get a recursion. And for the r star gamma, it will look like this. So at gamma is equal to 5/3, there's a change of function. So that's why the monotonic gas is a degeneration case. And in the phase portrait, it will corresponding to several 0 points. They will collapse. They will become 1 point.
Exponent of the solution when from the solution of the second form corresponds to the correct.
No, this is the limit. The r star is the limit. So the r star is where the k is infinity. So this ratio of the eigenvalues is infinity. And you will actually, in principle, have a sequence of solutions. And this corresponding to a sequence of parameters small r. And those are tends to r star. So in between any integer, so any r such that k of r is integer, you in principle you will have 1. Okay, you may see this more clear if I write down the next thing. So you do the Taylor's expansion. Around PS. So write down the W, because C is the summation. So because it's just ODE, you can always plug in and to use the recursion formula and use the low order Taylor coefficient to find high order. And you already have the first two fixed, which is V plus and V minus. This gives you the first starting point and plugging in. So one effect you can see is that the WM will be, well, this is a recursion formula, right? So it will only depends on the lower order Taylor coefficient. So this is just normal. And another one, there's actually may have a singularity. Which we write in an abstract way because all those things are super complicated. N minus K. So this is what, in some sense, will denominate the behavior. So this, when the R is chosen such that K of R is very close to M, you may get this. This thing tends to 0 and dm tends to infinity. So this will in principle be very large and change the behavior a lot. So they are actually a wiggling effect. So in some case, when it's close to m, it will shoot into one side, and it's close to m plus 1, it will shoot into another side. And the sequence is chosen such that the R sub n, so the possible sequence is between the K inverse and the K inverse. Well, not all of them are proof, but that's the possible sequence. So now we show that there's a sequence of them that may work. So now we can show a little bit more clearly about what's the people's results about. So basically there are two groups of results. One group is when the n is sufficiently large. So they are very close to R star. So in this case, what you can make use of is there's a limit R star. So you can do some expansion near R star to see what's happening. And another group of profile is, this holds for all the physical parameter gamma, is that they choose this R3 between the K inverse 3 and K inverse 4. So fix this range, and corresponding to R3, they find profile. So there's only one self-similar solution rather than a sequence of self-similar solution if you want to do the R is super large, the N is super large. So that's why people have two different groups of profiles. I will write down the results again. Here. very close to R star. And the results from the Tristan, Gonzalo, and Javi. So if you fix a parameter, then that's easier to extend it to all gamma. So that's they do for gamma grid between 1 to infinity. There exists C infinity smooth solution, just one for each gamma. So it's between R3 gamma to R4 gamma. So the R3, R4 is the where the this n is equal to 3. And for the gamma is equal to 7 over 5, they do it for a sequence. Yes. Yeah.
You can construct one solution.
No, you can, in principle, a sequence, but this is not, so for the gamma, but you want to do the full range, like you can do it, if you fix, in principle, you should find a sequence, but the thing is very sensitive, it's not very sensitive, you have to do it case by case because there's a complicated barrier argument. So if you do it case by case, like you fix gamma and you find the corresponding R, which in the range that you want, it will be done. But if you want to extend it to the full range, it's already very complicated. And
What's the difference between the two?
oh, these two. Oh, yeah.
You fix gamma. But the exist
A sequence. Oh, so the difference is that this corresponding to very large n. The second one is very large n, and the first one was n when n is equal to 3. Yes. So there are two different groups. So this one is fixed n is equal to 3 and do the argument, and this will use the renormalization near R star. So use the limiting behavior. And I think one thing to notice is for Navier-Stokes, this probably is the only thing that works because only when R is very close to R star, this Laplace can be treated as perturbation. There will be a bound. So yeah, but for this probably the Navier-Stokes doesn't work because this R probably is not large enough to give you the decay of the Navier-Stokes equation, the exponential decay of the Navier-Stokes terms. Yeah. But I think why they do 7 over 5 is that this is the diatomic gas, so it's a physical gas, and for their paper they don't know what gamma work and what gamma doesn't work. So it's in abstract way there's a 0 points of a function that it may not work. So that's why they do 7 over 5. That's my guess. Yeah. Yeah.
Regarding that
Yes.
zero set, does that have anything to do with the analysis on the board, or is it some other restriction elsewhere in the analysis?
No, there's an elsewhere analysis. This 0 points. Yes. It's not there. Okay. And then there's the results for the gamma equal to 5 over 3, the monatomic gas. So these are degeneration. Oh, but they do know the gamma cannot be equal to 5 over 3 because it's degeneration. Yes. So this is also a sequence of significant response profile. So when the R n is tends to infinity, the n is tends to infinity is near the point. So yeah, the only thing that I think is important is that there's a sequence of profiles that may happen, not just only one. And this corresponding to the delicate analysis near the PS and those barrier arguments, which are complicated, and I will not touch that. Any questions? Yes. I don't think so. The gamma I think when the physical meaning is when gamma is greater than 1, when gamma is equal to 1 is probably where some degeneration happening. So when gamma is equal to 1, then probably alpha is equal to 0. So and this looks like burgers. Yeah. So the first one will look like burgers, right? And the second one is determined by the first one. So I guess there's not a lot of things to be done here. Yeah. So how much time do I have? Oh, I have. Okay. So then we can start stability arguments. So the stability arguments, let's write down the equation again. So whenever it stops, we have this. So the dissipation that we wrote on the slides is depending on this. So we'll start from the stability of compressible Euler and then go to the Navier-Stokes. But I want to write here to see how the whole thing works. So for the compressible Euler, there's no these terms. And then you will have the linear term and the nonlinear term. So the most, in all such kind of stability arguments, the linear term is always the most important. Because there's a spectrum gap, and the nonlinear is just much smaller than the linear as long as your unstable mode is controlled. So the way to do it is, I will write down the compressible Euler. So there's only linear and quadratic. Well, never stop, we'll talk about later. Let's write down like this. Okay. So for the linearized operator, we want to show that up to a compact perturbation, it is a maximally dissipative operator. And I will write down the energy arguments for the dissipativity here. Let's see if we have time to finish all these arguments, hopefully. Maybe some terms, and we'll leave it some to the next time.
So NU tilde also depends on NS, on S10.
Yes, I just write it like that. Yes, of course, they are mixed together, so all the terms, yeah. So, yeah, here I will write this operator out, only the major term. So this is linear operator for U and the linearized operator for S. They're very similar, but not exactly. Okay. So now the finite codimension stability. So we did some cutoff to avoid the things at the boundaries, and also what we do is we project to the lower floor remote, but those are technical issues. So what I'm going to do here is a rough estimate that it's just an HK estimate, and to show that the highest derivative will be derivative of the highest derivative will be less than or equal to a negative constant times the highest derivative plus some constant times the lower derivative, and the lower derivative will be bounded by the compact operator. So that's what I will show. So this is the highest derivative if we take it in the homogeneous uplift norm. And this is less than or equal to a negative delta G over 2 of the homogeneous and plus some O. This can depend on M, which is very large, probably. So this will be controlled by a finite codimension dominator. Sorry, the compact operator, because this is a low order term. This this one?
Yes, just before this.
It's a constant. Delta G over 2. Well, just make it 1 to make life easier. It doesn't matter. Yeah, okay. You can choose M large enough so you can have 1. As you can see, this is all the lower term is modulo out. So the major term will only be these 2 terms. This major term, we call it mu. This is ms. So other terms are terms without derivative heating on our perturbation. So they are just controlled by a fixed constant times the homogeneous HM norm. So they are always good. So here's the proof. So the first part. So Lu minus Mu U tilde will be, let's say, equal to this is uniform, doesn't depend on M. And also the second part. So the Mu tilde and the Ms tilde itself is trickier because there are constant coming from the M, coming from the M derivative, and we have to fix or absorb a good sign from it. So we are going to treat it term by terms. For example, for the first term, this negative y plus u bar dot gradient u tilde. So of course you don't want to consider all the lower terms. So in principle, there are just two terms that is important when there's M, all the M derivative hit on here, or one derivative hit on the first terms, and M minus one derivative hit on the gradient u tilde, because this will gives you a large coefficient M, and this could be dangerous. So basically have these two things. So the first term is just the integration by parts. So it will be controlled by a fixed constant times the homogeneous HM norm. So let's call it 1.1. Just put one derivative here, and then this is bounded. The second one is potentially, depending on the profile property, it will either give you growth or decay. That's, of course, you have to mix with other terms, but you can already see it from this. So let's just neglect this M and do other things. So you have gradient y plus u bar dot gradient M u tilde. And you do it in L2 and with the gradient M u tilde. So what do you get from here? So you first split the gradient M into two parts. The first is M minus one derivative and one is another, because you split one into these parts. So have to make it distinct. So gamma prime is M minus one derivative, and you have alpha derivative. So there's another sign, summation over I, because our u tilde is our u bar is a scalar. It's this y dot gradient is actually the summation of ui dot gradient u. What you will get is here, partial alpha u bar I plus partial alpha yi partial gamma prime partial I u tilde partial gamma prime partial alpha u tilde. So partial gamma partial alpha is the derivative that you hit on u tilde. And for here, you put one derivative into alpha, and the I is coming from this y dot gradient. So that's how you split alpha and I. So this looks very complicated, but you largely rely on the radially symmetric assumption to simplify all this. So those are radially symmetric, and you can use this to change it a little bit. Now I will use another board. So one thing to notice is so what is this? This is partial alpha of UR plus R times YI over. This is the I components. Then the derivative will just follows, right? So because they are radially derivative, and you will have UR prime plus 1 when the derivative hit on the first bracket, and you have YR over R, YI over R. So those three terms. And you put everything into the energy estimates to see how it goes. So write it down. Y plus U bar plus gradient, gradient. Gradient. So this is summation. First, combining the first term and the last term. So U prime R minus UR divided by R times Y alpha YI over R. Did I miss a derivative? I think so. Oh, sorry, it should be R squared. I'm saying something strange. Yes. And then we have this partial gamma prime, partial IU tilde, partial gamma prime, partial RU tilde. This is the first term. And the second term will be UR over R plus 1. So that's our two terms, and now we simplify it. So we have the following observation that the YR over R, partial R is just partial R, and also YI over R partial I is also partial R. So So the first term will only give you radial derivative. Then and what about the second term? The second term only non-vanishing when I is equal to R. So this is in principle this thing. So you can get a radial derivative part from the second part and also angle derivative parts from second part. So you put them together and this will be a new coefficient coming out. So this gives you summation UR prime minus UR over R plus 1 plus UR over R. This is the radial part. And the angle part. I will just write partial system, although it may be a lot of directions. And so this will gives you the first part. So there's a slightly difference between the angle and the radial. So the difference is the first one is this coefficient. And the second one is this coefficient. So this is coming from the first term. And so if you go back to the, oh, did I erase the equation? Oh, I didn't. Good. So if you go back to this mu tilde, it's actually have a negative sign. And there's a m here. So when you go back to the original terms, it will actually give you a negative m times all those things. And so this is first part of the thing that will give you decay, right? Because there are 4 terms and there are other 2 terms will contribute to this coefficient. But you already can see that as long as this coefficient is positive, you should get a very negative term when m is very large. But this is just first term, and the other terms will change the brackets to really make this 2 bracket into the angle repositivity and the radial repositivity. Oh, we have 6 minutes. Maybe don't have time to write down all things. I will write down all things in the next lecture, but I want to write down the eventual results, maybe to just get some view of how things going on. And then we'll keep on doing this. So you already can see from this fact, but in the end, what you will get is this. Gradient m tilde mu plus this tilde. So this will be the summation. over gamma prime. So we will have extra contribution from the mixing term. And this is same for all the radial and non-radial direction. Sorry, I used partial gamma, so this is partial gamma. So that's how the final, of course, plus other bounded terms. So this is how the final looks. So change the coefficient a little bit. So this 2 will gives you this 2, and the mixing term will gives you alpha times absolute value of partial alpha s prime. Yeah. So 1 is actually coming from here. Is alpha s bar, and another one is coming from here. And all the terms that you have more than m plus 1 m derivatives, we will deal with by integration by parts. This is execute energy estimates. Yeah. Yes, those 2 are positive. Those are the profiles property. They should satisfy. Yes. Yeah, in dimension D, it's in the only it is positive in a critical region, and after that you can use. So this is in the work of Judge, how this Golomb couple. You can use this weight to kill other things. So if you put weight, you can further modify it a little bit. So you don't need it to be positive everywhere in principle for the fluid equation. But for the Schrodinger equation, you cannot add weight in the highest level energy. So this should need to hold globally. Okay. So I probably will stop here for the morning session, and I will keep on writing all the estimates later and how to deal with nonlinear and unstable things.
Are there any other questions?
Yeah. Yes.
The blow-up profiles we get, so we get these families depending on
Gamma. Yeah.
Do they all kind of roughly look similar? Like, do they all just look like bumps, or do they have oscillations to them?
Well, I didn't use numerical to see how it works. Well, the density tends to infinity at the middle, right? So there must be a bump. Well, except that I don't know. Yeah. Yeah, but in principle, you can do the numerical simulation to see how the profile look like and how they works. Yeah.
Any other questions? Well, let's thank Jay one more time.
Yeah, thank you.
We will reconvene at 3 o'clock for.
Yes. Hi. Oh.
Because you're doing dimensions, so what do you just
Oh yeah, I didn't know. I didn't write on details, but well, this estimate is actually so all those things when linear estimate is done with some power of some weights. So the table will be very true. But in principle, yeah, in principle, there's homogeneous system. So when you take more derivatives, they're actually getting faster. So it will be.
So this decaying time.
Oh no, decaying space.
This space, okay.
Are you?
No, I'm talking about.
You mean time?
Yeah. So you have.
In time, they have finite potential. Yeah, exponential except finite potential.
Okay.
That's the decay.
I see.
Yeah, you're right. Okay, so you can do restricted.
So this what you meant by stability.
Yeah, just the asymptotic
Stability, yeah.
Finite potential.
Coordination forecast. Thank you.
This is the